Hey everyone.
Hey, how you doing?
Good, good. Hey Chang, great to meet you. Really
Good to meet
excited.
you as well. Thanks.
Usually it takes a minute or two for folks to trickle in, so let's see. All right, James, do you want to kick us off? I think we can get started as we wait for folks to come in.
Yeah, that's great. Perfect. Give me let's see, share my screen, then we can get started with speakers. Perfect. Yeah, so welcome to Multimodal Weekly. This is our webinar series hosted by the team at 12th Lab with a focus on progressing the field of multimodal AI. So we've been meeting every Friday at 1:30 p.m. Pacific time over the past 12 weeks. So here's some of the topics that we tend to cover every week, research topic in the field, application in different verticals, interesting projects that our members want to share, industry technologies, and sometimes tutorial guides from our teams over 12 apps. This is a list of some of the speakers from the past session, origin topic from vector database to public audio processing to robotics to healthcare application. So for the session today, we have two speakers, Chang She and Haotian Liu. Chang is the creator of LanceDB, and he will talk about how to do data exploration and data management with the Lens format. I got a chance to watch his talk back at the Databricks, right? Database AI Summit back in a few months ago, and also we connect via Zoom as well. And definitely super excited to kind of hear more about the technical design of the project and how it have support with multimodal data format. And the second speaker, with more focus on the research side of things, is Haotian Liu, currently a Ph.D. student at the University of Wisconsin-Madison, and he will talk about large multimodal models that follow human intent. He's quite accomplished researchers with some of the work like React and LLaVa, and both work sort of help push the field of multimodal AI, specifically with the new design of a large vision language model. So super excited to kind of hear the origin of how those research get started and how it's going to evolve in the future. Quick note on the logistic, feel free to send your question on the chat, and we'll have a Q&A session once both of the talks are finished. So with that, I'll let Chang start with first, and you can start sharing your screen.
Sounds great. Hey, everyone. Thanks for having me on. Very excited. Let me just get the slideshow going. If you guys have trouble seeing anything, please speak up. Cool. So we're going to talk about managing multimodal data and managing unstructured data. So that covers anywhere from traditional tabular data to kind of metadata to vectors, images, videos, point clouds, and the whole gamut. Everything that you would need as a data layer for AI. So a really quick introduction about myself. My name is Chang. I'm co-founder of LanceDB. Once upon a time, I was a co-author of the Pandas library, so I've been working in ML tooling for more than a decade now. Most recently, I was a VP of engineering at Tubi TV, where I focused on ML ops, the recommender system, and also experimentation. So if you want to talk shop on technical topics, find me on Twitter or GitHub by the same handle here, which is also my AIM screen name. So I'm dating myself a little bit here. So a lot of people kind of ask me, why I created a new data format this was in 2022. So, it's a little bit crazy to say, hey, we need a totally new data format. And the motivations behind it all was the pain that I saw at Tubi, and also my co-founder Lei saw at Cruise, for enterprises managing large-scale unstructured data. So the pain points can be summed up in sort of 5 buckets. One is bad performance during training, and a lot of this is not just straight up data loading, but you might want separation of compute storage. For example, you want to store your data in cheap object storage, but you want to quickly load it into your GPU machines. Or you want to be able to quickly shuffle the data as you're training, or slice and dice and filter that data before you train. On the other side, once you have the model, you also need to do debugging or evaluation or analytics. And slicing and dicing your data set and then drilling down into a problem scenario or an edge case is not easy. And the existing data formats doesn't support doing that very well on these large blobs. So as a result, what happens is that a lot of companies that we come across just don't have a single source of truth when they have to deal with unstructured data across their AI lifecycle. So typically what we see would be something like you would pick one format like Parquet or perhaps TF records. That's your main format. And then you end up having to have different copies of that same data for different purposes, whether it's for analytics or training or debugging. And then you have to stitch all that together, and you have different code and different compute on top of these different sources. And then on top, you might build a shim layer that's fairly thin that tries to pretend that it's all sort of one system. And part of that problem then becomes not only do you have to have multiple copies, but your tabular data, which tends to be like your time series data or metadata, has to be stored separately from your actual unstructured data. So this creates a lot of complexity, and it makes things a lot harder. And also it really blows up the cost for data lakes for folks through data duplication and for the amount of compute that they have. So we decided to create Lance to solve the pain points in these problems. And Lance is a file format, it's a columnar file format that is specialized for multimodal data and also for nested data that we need in AI. And of course, you can still store tabular data and get just as good performance. And so as a columnar format, you can think of Lance as a replacement for Parquet, right? But Lance is also a table format where we have Lance datasets. So it supports transactions, it supports secondary indices like vector indexing, for example, and has this great zero copy versioning where you can add columns, add rows, delete rows, do updates, and do schema evolution without having to create duplicate snapshots. And for our users, especially that are storing lots of large blobs, this is actually very important because duplicating 2 petabytes of image data is just untenable, right? And so as a table format, you can think of Lance as analogous to, say, Iceberg or Delta and similar technologies. And Lance kind of combines these two into one package that's very lightweight. It's built in Rust and has Python bindings, and also we've built a vector database on top that has JavaScript bindings as well. Today, Lance is used for a variety of use cases. We're the fastest growing open source data format. Our users tend to be in a few buckets. One is large scale data mining for autonomous vehicles. And this allows you to do something like OLAP style, like SQL or simple data frame operations to do complex data mining over very deeply nested autonomous vehicle sensor data. So this is a combination of time series data that comes off of instruments with the metadata plus the imaging and LiDAR data that is coming off the actual sensors. A lot of folks are using Lance for generative AI across both inference and also the data lake. So we've got users with petabytes of image data that are in the process of swapping out their entire storage layer for Lance format. And they're seeing performance gains across the board from training to analytics to debugging. And then lastly, I think vector databases have become more popular because of generative AI, but traditionally they've also been extremely popular in recommender systems and search engines. So a lot of our users today are in sort of the e-commerce consumer application space where we have billions of embeddings generated by models, and we can do real-time serving at low latency at incredible scale on just a single node. Lastly, in terms of integration, what I wanted to talk about is, I think times have changed. When Parquet was first being developed 10 years ago, it was incredibly difficult to get adoption outside of Impala because you have to build these pairwise integrations with a lot of different tools. But today, because of Apache Arrow, it's actually very different. So we built our main API and that means out of the box, Lance can be compatible with tons of tools without any knowledge or additional effort on the part of the user. So you can use Lance data in pandas and polars, DuckDB, PyTorch, Spark, you name it. If it's Arrow compatible, it's Lance compatible. The additional, and one more advantage here is that data migration is super simple, right? And migrating from Parquet or TF records to Lance is literally 2 lines of code. One to read it into Arrow and one to write it into Lance from any format. And the same is true vice versa. Right. So before I dive into the core design, just wanted to show you a quick application that I've built using Lance. Right. So I've got LanceDB, which is a vector database that is built around Lance, and I'm going to use PyTorch and Gradio and sort of transformers for this one. So I've got a data set that has YouTube videos with some metadata and embeddings that I've generated previously for the sake of time at the frame level. So not nearly as sophisticated as what you guys are doing here. But I basically create a LanceDB table and open that here. And then I'm going to use CLIP as a very simplified example here to embed the text queries that you might enter, right? And then we're going to build a simple little Gradio app that looks like this. And so you can type in just type in a text query here. You can say like, I don't know, cooking shows or something. And then, and this is the code that you would need to run to search through your database, through your LanceDB, to find videos that are related to, cooking shows or something like that. And then of course you can play it and it'll search through it and find the right segment where it starts. And then of course, what's interesting about Lance is that it's not just good for vector search, but because it's a columnar format, you can run very flexible workloads on it. So you can actually So you can actually run just queries, SQL queries, say, select distinct star form videos where, I'll just call this like limit 9. And here I'm using DuckDB to search over this data set, and I can return and view the videos as I see them. So let me stop 1 second. I think, are there a couple of questions? Oh, I see. Okay. I thought there were questions. All right, cool. Okay, so any questions so far? If not, I can keep going on the core design. All right, great. Keep going then. Okay, so let's talk about Lance. Right, so in the demo, what you saw was it was very simple to build this application because all of your data is stored in one place, and the data set itself supports a very flexible, a very diverse set of queries that you can run on it. Right? And so what makes Lance format different that it enables this? Right? So one is one of the biggest differences is that Lance is designed to be fast for both analytical scans and also random access. So other formats like Parquet, for example, is only good for one, but not the other. And for AI, turns out you need both. And then other formats like Parquet are not optimized for storing large blobs. So if you have image frames that you're storing or point clouds, it's very difficult to deal with them at scale with Parquet format. And the I/O execution plan for large blobs is also optimized. So when you run a SQL query and the pushdowns that go into the format and the I/O level, it's very different because we make different assumptions about the characteristics of the data. And so we can take advantage of parallelism much more than you would expect a Parquet would do for tabular data. For versioning, right? So what Lance does is it uses metadata to be able to put together different files and support reading and updates after schema evolution. And all this is I call zero copy because you don't have to make snapshots. You can do append rows, append columns, remove columns, do updates, or do row level deletions. Updates are just a combination, again, of deletions and appends. And then on the roadmap is a write ahead log so that we can have much faster real-time data in the index updates. Last thing I'll mention about Lance here is the secondary indices. It's actually a nice side effect of having fast point queries. So the first one we've implemented was a dispatched ANN's index on vectors. And by having index and the data living together, we can give people much faster performance, much better scalability, and just overall easier tech stacks. So let me show one more really quick example. So I hope you guys can see the print. So I'm going to import LanceDB here, and I'm going to connect to an existing database on my local just MacBook laptop, right? And so I've got a table called test1b, right? And so this table has 1, 2, 3, 4, 5, 6, 7, 8, 9, so 1 billion vectors in it. And I'm going to create a query vector using NumPy. Whoops, I need to, query vector using NumPy. And then I'm going to run, I'm going to time the search. So I'm going to search using the query vector limited to 10 to arrow. And then I'm just going to run it like a bunch of times in a loop and take the average. Right? So once it finishes, it's going to report the average time. And so as we can see, we're able to search over 1 billion vectors just on my MacBook in under 10 milliseconds. So this is pretty fast. And I'm not sure I know of another vector database or data format that supports this type of scalability and performance. All right. Let me jump back to the presentation. I think I'm pretty much done anyways. Quick here. Yeah. So certainly we've got loads of really interesting features on the roadmap. We're working on optimizing our disk and index performance. There's lots of advanced sort of data format features that are on the roadmap. And we're going to be working on improving our Spark and TensorFlow and Ray integration as well. So thanks for listening. Would love for you guys to try this out, as your feedback's super important to us. And if you like us, consider giving us a star on GitHub. That's it. Hopefully I didn't go over time too much.
No, yeah, you're still on time.
Okay, great.
Perfect. That's one question from Tony about integration compatible with PyTorch DDP. Can you address that?
Yeah, yep. It is compatible with PyTorch. I think we're going to be building more conveniences for like filtering and things like that on to make that integration even smoother. But today, people are already using they're building PyTorch data loaders and things like that on top of Lance. Thank you.
Yeah, actually, I have also a question, but maybe it was in the roadmap. Does Lens support partitioning? Because with Parquet, especially with very large files or like tables, usually instead of query the entire table, I can partition by a certain like feature, and that speed up the process. So I was wondering if Lens supported.
Absolutely. So it is on the roadmap. We're actively working on it right now. And so not just being able to partition, but also being able to compute the stats for each partition. So when you run a predicate, for example, like a filter, we can use those stats to then prune a lot of the partitions. So the performance of like predicate scans can be a lot faster as well. Yeah, great question.
Cool. Thanks.
Yeah, I guess maybe one or two more questions before we move to Haotian. Let's see. I guess I can ask questions. So use cases why, like, I think you have a slide about data mining for ED, Gen AI, and e-commerce, right? Out of curiosity, like, what do you think? Can you share a bit more details about like the sort of applicability of Lens with like other form of multimodal application, and what are you personally excited about for this use cases?
Yeah. So maybe I can share with you like one use case in autonomous vehicles, right? Just as a more specific example. And so I don't know if you guys remember, there was Tesla had an accident on the Bay Bridge like a few months back, maybe 6 months back or something, where like the car slammed on the brakes when it wasn't supposed to on the Bay Bridge, and there was a crash, and like I think somebody was killed or something like that, right? And so as soon as that happened, one of our users that was like an autonomous vehicles company came to us and was like, holy crap, we need to find all the similar edge cases in our data and try to add those to the training model, right, to overcome those problems. And so then the problem they had was, okay, you've got data that's coming off the car that was like time series data in protobuf, metadata in whatever format, and then there's like a bunch of images and all that. And so to help them, essentially we would essentially help them write code to unify all that data into one data set, or like one sort of Uber data set. And then instead of having to write these complicated jobs and scripts that runs really slowly, what they could do in the end is write simple SQL queries that express the data mining logic in simple terms and go from like, running these data mining scenarios in like a week to like an hour.
I see. Yeah, thanks for fleshing out on the details. Yeah, maybe one final question, just out of curiosity. So you experienced working in pandas, right? Back in the days, and obviously it's a very, very popular open source framework for Python developers. So I guess like, given that experience, what do you think? What drives the success of that project? And what do you think can be applicable, translatable towards plans? Your current journey?
Yeah. Yeah, I mean, I think a lot of it was, I think open source projects, it's very easy to just start putting things over the wall without talking to users or without understanding the problems that they have. And so the danger is you're writing code that doesn't solve anyone's problems. And so I think that was one thing we got right initially in Pandas. It started out just solving our own problems, because I was as a quant, and Wes was also a quant in finance. And so a lot of the initial design and features in Pandas was geared towards solving like portfolio management, data loading, data engineering, and finance. And once that became popular, then a lot of other communities started to use it. And then we sort of branched out into those communities. So I think the biggest lessons there are, make sure you're talking to users, engaging users all the time, trying to make sure you're solving the real problems. And then also sort of making sure you solve one vertical well before you move on to another. I think that helped as well. So those are probably like the big lessons that I take to heart a lot developing Lance now.
Awesome. Yeah, thanks for sharing that insights, and super excited to see the progress with the project, and potentially discuss ways to work with 12 Labs and kind of pushing some of the work on video embeddings that we've been working on.
Thank you. Thanks for having me.
Do you mind, James, if I ask another question?
Yeah, sure. Yeah.
Okay, cool. Thanks. So if I want to use Lens on Databricks, does it leverage the distributed system of workers, or it needs to push everything on the driver? Because for example, when I'm using PySpark and then I want to convert the PySpark data frame into pandas, it pushes everything on the driver, which basically it loses the capability of leverage the distributed system offered by Databricks and its backend. So I was wondering if Lens allows that.
Yeah, so one of our users is doing sort of what you're describing. They're using Lance, or they're using PySpark to create very large Lance datasets. So essentially what they're doing is spinning up a bunch of nodes. Each node is responsible for generating like a single Lance file, essentially with what will be a partition, right? And then at the very end, on the driver, there's a commit process that creates a new version of the data and makes the new version and the new written data file is readable. So I think as long as you know what kind of operations you want to do on the driver and keep that fairly small, because just like making a commit and writing metadata is very small, and you don't have to crunch through all of that data, then it's still you can take advantage of all the parallelism that Spark gives you.
Okay, but if I understood well, at the moment it behaves like more pandas data frame, so everything is loaded on the driver.
No. So so you can, I mean, with PySpark you can control what you read in the driver versus the executors, right? And so what they're doing is in each executor, they're actually writing the Lance data and operating on the Lance data. right? And then it's just on the driver, it's just a simple like metadata commit.
Okay. Okay, cool. I will check it out definitely. It seems really cool library.
Thank you.
Great question, Matthew. Haotian, do you want to start? Unmute and sharing the screen.
Oh, sure.
So excited. Yep, I can see it.
Okay. So maybe I'll just start.
Yep, go for it.
Okay, so hi everyone. Today I'm Haotian Liu from University of Wisconsin-Madison. I'm going to talk about how we view large multimodal models that follows humans' intent. And I'm going to briefly talk about the background of large multimodal models and how we do instruction tuning in large multimodal models, and a little bit about the future work that we're interested in working on. And so first, a little bit about the background, where like what is a image to text generative model? What is a multimodal model? Basically, the goal is to create a model that accepts image inputs, and then it can try to demonstrate its understanding of the image by outputting some natural language. And to do this, there are usually two ways of the pre-training approaches. One is to create by leveraging those large-scale image text pair datasets like Leon, and you feed the image to the language model and let it predict the associated captions. And by training in this way, the model somehow learns to connect the image and the language modality. And when you ask the model about those image text questions, it will be able to demonstrate its understanding. And some of those models include BLUP2 and JIT. The other approach is to create those image text pairs in a sort of like interleaved format, so that you have image 1 and you have some text that's related to this image 1, and you have image 2, text 2, and when you have image 3, you feed all of those previous image text pairs into the model, and that the model to predict the text of the third image. In this way, you somehow elicit the so-called in-context learning of multimodal models. As a result, for example, you train the model in this way, and when you test it, and it can have some like interesting capabilities, like doing a math. For example, if you feed in like the image that contains those writings about a math equation like 2 + 1, and you also provide it with some answer like 2 + 1 = 3, and give it some examples, the model somehow knows that what the task is, and it leverages its pre-trained knowledge to complete the task of the third image. So it guesses that, okay, you want me to recognize the characters in this image and then do the math. So it outputs 3 × 4 = 18. So these are amazing capabilities, but usually the questions are quite simple and are just like single turn direct reasoning questions. And this year in March, the release of Multimodal GPT-4 actually impressed a lot of people with very strong visual understanding and reasoning capabilities on a variety of tasks. For example, it can look at this image of the man ironing in the New York City standing on the back of the taxi and say that just directly pointing out those unusual things. It can also understand those memes that we usually see in the Twitter and explain what's humorous or what's interesting about those memes. So those type of the reasoning capability is much stronger than those previous methods. So we just want to know, like, why is that so capable of the previous methods, and how are we going to build a model ourselves that can have some sort of the capabilities to those degrees. So we ask these questions, and we believe there are several important components that we need to make sure that we have. So first is that you need to have a strong pre-trained vision and language models, which can serve as the backbone for your final multimodal model. The vision model should be able to understand the image, being very capable at understanding image details, and the language model should be able to accept those information and reason about it using its pre-trained open world knowledge. And you need to have a very flexible connector to connect those two modalities. And also, you need to tune those this resulting multimodal to learn to follow the multimodal instructions. So like we are going to talk about the third part first. So before we move on to the multimodal instruction tuning, we first explain what is instruction tuning in language models. So basically, we pre-train the language models on trillions of the tokens, and the model can actually know lots of knowledge of different domains, including science and also literature, laws, all kinds of the domains. But it does not necessarily can understand the user's request yet. So to do this, instead of still training a huge amount of the data, people in natural language processing domain find that you can just provide it with some simple instruction input and text output pairs. So you tell it that like the task is to explain the human's behavior, which is crying, and then give it some example output. By doing this, the model somehow learns how to leverage its pre-trained knowledge to follow the way that the human wants, which is like following the human's intent. And you do not need to train a huge amount of data, but just to use those kind of data to guide the model how to think. And by doing this, for those unseen new tasks, like how to queue a Docker container, the model can leverage two kinds of the knowledge. Like first, how do we think during this instruction tuning stage? And what is a Docker container? And actually how to queue the Docker container? For those kind of knowledge, it's actually contained its pre-training stage, which is a huge amount of like trillions of the tokens. So now by combining these two kinds of the knowledge, it can answer this question very well. And how do we collect such instruction tuning data? Like there are generally two ways. One is just to use human annotators to annotate those instructions, which is at a high cost. And the other way is just to use strong language model-based teachers like ChatGPT to generate those instruction and output pairs. And this will be of affordable cost. And the way people do this is from self-instruct, is that because language models can have strong like in-context learning capabilities, it can guess what the task is based on your previous inputs and outputs. So basically what you do is that you just write a small set of the tasks, like explain the behavior and like some reference answers, some new tasks, and give some reference answers, and just tell the model to generate new instruction input output triplets that meet the following requirements and learn from those previous examples. By looking at those examples, the model actually knows how to generate new instruction input output triplets. So in this way, you leverage a teacher like ChatGPT, use a small set of those seed instructions, like let's say 100, you can expand it to tens of thousands or even hundreds of thousands instructions with, I think, I think in the self-instruct paper, they say that it's just hundreds of dollars. And if you collect with human, it will be much longer time and also much higher cost. And after the introduction of those GPT-4 ChatGPT, there are lots of open source models that's built upon the Llama and Llama 2 to create. They create instruction source and fine-tune of those instruction tuning data sets and exhibits very strong capabilities that is comparable to those models like ChatGPT-4, GPT 3.5, or Claude. So those results are impressive, and we want to know like how can we build such models for multimodal domain. And we present our first attempt in this area, which is visual instruction tuning. We want to bring visual instruction tuning to multimodal stage. And specifically, what we're going to do is to have the image and the instruction about the image and some designated output. And we're going to have this simplified architecture where the image is feeding to the visual encoder. It's connected into the cross-modal connector, connected to the language decoder using this cross-modal connector. And the language decoder will accept those transform the features from the image encoder as well as those instructions, and it will leverage this pre-trained knowledge to output those understanding of those images. So how do we do that? There will be two key components that we need to figure out. First is that to train the model in such like image instruction output triplets, we need to have such data set. And how do we construct this data set? Can we use some protocol that's similar to self-instruct to do this? The second is, how do we design this cross-modal connector? And let's first answer this first question. Reviewing those previous instruction tuning models in language models, we actually find that those teachers are mainly GPT 3.5, GPT-4. All of those teachers are actually text only, meaning that they do not accept image input and they do not have image understanding capabilities. Although GPT-4 has demonstrated this, they do not release their API yet. Also, like the recent Bard and Bing Chat, they do not have API yet. So actually, we are not able to utilize those multimodal teachers. And so how when there such teachers are not available, how do we create such data? And we find that there's actually a simple idea that can allow us to do this. So let's suppose that we want to feed this image instruction output triplet to the language model. How can the language model can of course understand instruction and output. The key point is that how to let it understand the image. And we find the simple way is to provide some description about the image to the language model. The first type of description can be just some short captions describing the main things that's happening in the image. For example, a group of people standing out of the black SUV with some luggage. And you can have more describing different aspects of the image. Another of the type of the context is to use a layout, which is you draw some bounding box of those objects, and by looking at those objects, we can like the model can somehow imagine about what the scene looks like. By combining these two kind of the context, the model can have a sense of most of the information that's contained in the image. And the bounding box can be represented in plain text. So actually like these two type of the representation of the image can be understood by at least GPT-4. And fortunately, these two information are actually already available in the commonly used MS COCO dataset, where each of the image are already associated with 5 short captions, and it has annotated bounding boxes by human, where each of the bounding boxes are associated with object categories. And by leveraging these data, we can now use the same self-instructed pipeline where we feed those context in the textual format, the instruction output, and we can have a set of those examples of how we utilize the context to create instructions. And then just ask ChatGPT, like, now we have a new context, which is a new image. Can you generate the new context instruction output triplets for me? And there are some requirements, and GPT-4 will just learn from those previous examples and generate new instruction and outputs for us. And to make our generated instruction tuning dataset like more diverse and more controlled, we create 3 types of the questions. First is the conversation, which are just like short question answering about different aspects of the image. The second type is the detailed description, where we try to let the model to describe all the details that's contained in image, so that it somehow learns to reason about all of those details in the single image. The third type is the complex reasoning, which we try to make the model to think about those more complex tasks, like what challenges do these people face? And in order to understand this, the model will first need to look at the image, understand all the things that's happening in the image, isolate the relevant details, and then tell the user, respond to the user, like what they're doing and why are they facing what challenge. So basically, we want the third type of question to use the third type of the question to enforce the model to display those GPT-4 level complex reasoning capabilities. And by using all the mentioned pipelines, we are able to create a LLaVa instruct 158K, which contains 58K conversation data, 23K detailed description data, and 77K complex reasoning data. Okay, so now we figure out a data set, then it's about the model. And actually we find that creating such model, cross-model connector is actually quite simple. We just use a single linear layer. And so now let's make this architecture more concrete. So we have the image passing through the visual encoder and the projection layer, where the vision encoder is just a CLIP vision encoder, and the projector layer is a linear layer. We combine the image features after those layers together with the language instruction, and just feed those into the language model and train the model to generate the response. And the language model can be Vicuna, Llama 2 Chat, MPT Chat, all the kinds of those open source models or pretoric models that are pre-trained to follow instructions. And the reason why a linear layer can work is that because when we train CLIP, when OpenAI train CLIP, we do not train the CLIP. They trained it with image and text pairs. So they train it with image text contrastive learning. Basically, they try to align the image encoder outputs, the features, to align with the text encoder outputs of those captions. Basically, their image encoder features are already in a distribution that's quite aligned with their CLIP text encoder distribution. So we find that because this already aligned property, we just need a single projection layer to realign this to our Vicuna language distribution or like Llama language distribution. So that's the reason why it just need a single layer. And specifically about the training detail is that we now train it in a two-stage fashion. The first stage is just we train this projector layer only just to make like train on a set of image caption data set, so that the language model now actually knows the output of the vision encoder. In other words, like the vision encoder is now aligned to this language model distribution instead of the original one. The second stage is to leverage our created LLaVa instructor 158K data to answer those open-ended, user-oriented visual tasks, like those like daily tasks that involves image that we may use to chat with ChatGPT. And also we try to incorporate another dataset called Science QA, which is a multimodal reasoning dataset for the science domain. So after train such model, we actually find that despite we use a very like small scale of data, which is just like 600K and 158K, we find like the model actually has a lot of interesting emerging properties that's actually beyond our training data. So before we dive into those examples, I would like to first share a little more details about our training data. So we pre-train on a filter set of CC3 million, and we instruction tuning on the data that's constructed from COCO. For these two data sets, they like CC is the short for, I think, common concepts or concept captions, and COCO is just common concept. So basically these two data sets are about those common concepts, and this means that they are only covering a very limited domain. Second is that in both of the data sets, there are no explicit human name annotations in the data set. So, and the third thing is that there is no explicit OCR data, which requires the model to recognize the text. However, we find that by training those data, there are some interesting capabilities. First is that we find that the model has the strong visual reasoning capability, and we just use the examples in the GPT-4 paper to see. And our model is able to like see that the unusual aspect of this image is like the man like standing on the back of a minivan and ironing those clothes. And even when we just like directly ask what's happening in the scene, the model is able to identify those actions like ironing the clothes, and also it can identify that this behavior on top of a moving car is actually unconventional. So it seems like combining those detailed description and the complex reasoning data together actually makes a model reason about the complex scenes, even in those like, I think it's more like a detailed description task. So it's a very quite impressive and encouraging result. The second is about the chicken nugget map meme in the GPT-4 paper, and the model can, as I just mentioned, that we do not have OCR data, which requires explicitly train the model to recognize those text, but it actually can say that the meme begins with a phrase like "star." Sometimes I just look at the pictures of the Earth from the space, I marvel at how beautiful it is, and it actually try to reason about the humor, why this the nugget looks like the Earth. Different nuggets may represent different continents. Although there are some small hallucinations, saying something like there are other text in the bottom, but yeah, well, we think those emerging properties are really interesting and encouraging. And those previous models like BLIP2 or OpenFlamingo, they are not trained with those complex reasoning instruction data sets, which we find to be crucial for eliciting the model capability of reason about those complex images. And the third is that for those this parodied Mona Lisa image, it's actually be able to reason saying that this is a dog posing as the same pose as the Mona Lisa, and this may be some creative humorous take on those iconic painting, really out of domain images. And this is even more out of the domain where we have no human annotations. And this is a meme that we in-paint the Elon Musk into this meme, and it's actually able to recognize the names of those celebrities. And OCR capabilities where it can recognize the characters and reason about it, and also about the reason release the Llama 2, and also say that it's people interested in Microsoft and Meta collaborative projects might be intrigued. So all of those capabilities are interesting. And we just want to know so how do we evaluate them? How do we evaluate those large multimodal models? And we find that we can just simply modify our evaluation pipeline, data creation pipeline to make it evaluation pipeline. So basically we just feed those contexts to the GPT-4 saying this is the image, this is the instruction, and here are two model outputs. And which one do you think is better and why? And the GPT-4 can actually give scores and tell you why he gives this kind of score. And we use this pipeline to benchmark on the COCO, which is in the same data distribution as our training. And we find that the training actually goes on quite well, and it can achieve similar, around 85% of the relative performance when we feed GPT-4 with the ground truth annotations. And to make a step further, we also create those in the wild data set where we create those, we find those images from the internet, and we annotate them with very detailed annotations and create those more challenging tasks that requires knowledge beyond the training data, and sometimes even multilingual understanding, or you need to understand about the subtle details. For example, one question is, what's the brand of this blueberry flavored yogurt, which really needs you to zoom in to find it, the brand. So we just create this data set to make it challenging for the models to work on. And we also find that for some of the knowledge, you may need new capabilities, so that you may need retrieval from the internet. And those kind of capabilities are what we want for future multimodal models. And we also use this benchmark to test the behavior of the newly released models like Google's Bard or Bing Chat. And our model is actually doing surprisingly well. And in some categories, they are comparable with those models, which is actually a big system. And because some of the because Bard and Bing Chat currently will refuse to answer questions about human, we also provide some numbers that are without the human faces, so just to remove the effects of those models. And we recently also introduced the LLaVa Lightning, which allows you to train those models with better scalability and accessibility. Basically, you can train our model with both stage training in the instruction tuning and the pre-training using 3 hours on 8 A100 or even just 6 hours on just academia common GPUs like 3090s. And basically the way we achieve this is to use the SPLIP caption delay on dataset, which is at similar scale out of our dataset in the paper, but has a much broader concept coverage. And we fine-tune with the smaller LLaVa instruct 8K with 1 epoch training schedule, which we find to be sufficient for the model to be capable of performing well on different tasks. And we can also do LoRa or QLoRa training, which we test to be having similar performance as full fine-tuned version. With you may do it like if you use LoRa or QLoRa, you may just need 4 A6000 or 8 3090s, and without the need of CPU offloading. And yeah, so the cost is smaller, and we hope that this can make those model training more accessible to both academia and also startups. And we have release checkpoints for using Lightning schedule, like just 1 day after the MPT's release and the same day as the Llama 2's release. And we have benchmark on the LLaVa bench in a while to ensure the quality. And since our release, there are huge number of efforts in the community on those large multi-models. And specifically, we do want to emphasize the efforts on the benchmark because we believe that the benchmarks will be important to ensure the quality of our models. And there are currently 3 different types of the models, benchmarks. One is like those close-ended, more like yes or no or multiple choice questions. And the second set of the benchmarks are using some predefined questions and using the GPT-4 or human to evaluate those responses of the models. The third type is the open-ended online evaluation, which is more like the arena, where like motivated by the Vicuna arena, where people will actually ask 2 models the same question, where you cannot know which model it is, and you compare the answer and rate which one is better. And actually, like in this setting, LLaVa actually the response of LLaVa are preferred against the other language models, including the ones that are coming out after LLaVa. So also by looking at those benchmark results, actually there are 2 key limitations of LLaVa. First is that we still suffer from hallucination, where it may say something that actually is not happening in the image, and also it may not be able to output the specific format requested by the user, which is needed for standard benchmarks, where you just need to output a single word answer, but LLaVa may just fail to do that. And although we have done impressive progress, but we are still not here yet with like GPT-4's performance, where it can do complex math and summarize those multi-page papers, which you will require the model to access to both the high resolution images, and also the language model itself should be capable enough to do those complex math questions as well. So here are 2 sets of future work that we're interested in working on regarding the capability. We want to reduce the hallucinations. We want to work on higher resolutions and how to align the models without forgetting the NLP knowledge, and how to do those high resolution multi-image understanding, and how to make your knowledge really infinite by retrieving information from the internet. And regarding the understanding, we do want to understand why those emerging capabilities like OCR emerges, and can we actually magnify those behaviors to make it even better by understanding why it happens, and how do performance of the language models can affect the capability of multimodal models, or whether those reinforcement learning tuned models like Llama 2 can behave differently from the ones that just tuned with instruction tuning. So these are all the future works that we're interested in working on. And yeah, thank you for the invitation for a talk. And here are some recent updates, and you can try out our demo or refer to our paper. Yeah, thank you so much.
Fantastic. Thanks, Haotian, for going about this in depth.
Yeah.
This process of creating LLaVa from the process of creating instruction from data set and some of its strong capabilities to the evaluation benchmark, as well as some of the future roadmap that you have for the project. Yeah, we've been gone a bit over time, but would love to have folks in the call to ask any questions for Haotian if they have any.
Sure.
I have a question. First of all, thanks for the inspiring work. I love it. I think everyone in this field probably already knows LLaVa, but thanks for the really nice presentation to go over every concepts. I have two questions. One is, when you train the model, where do you see the information bottleneck coming from? Do you see it from the data, or do you see it from within the model architecture, visual encoder, or large language model? So I was wondering where, as you train this visual instruction tune model, where you see that bottleneck. And my second question is do you think there is this particular data type within that instruction tune data set that's contributing to this emerging ability? For example, you define it into 3 categories, I think: conversation, complex reasoning, and detailed descriptions. I was wondering if there's a specific category that really contributing to that emerging capability.
Yeah, thank you for the question. These are very good questions. So for the first question, I think this actually varies case by case, and different challenges actually we will see different bottlenecks. So for example, if we have internally tried to vary the language models, and if you just ask it to answer let's say some math problems, and it may know what you are written in the image, like the math problem itself, but it does not have the capability yet to actually solve the math problem. And for these kind of questions, those challenges, actually scaling up the language models, from Llama's 7B to 33B, or even the largest one, we can actually see a big gain in terms of that. But there are also challenges how to recognize very small characters, recognize small objects. And also, for those kind of questions, you may need to scale up the vision encoder, where we actually see that when we scale up the input resolution from 224 to 336, can actually give a huge boost to these kind of questions. And the third challenge comes from the data, where there are actually 2 challenges. The first challenge is that how to let your multimodal instruction to really follow the intent. And the one specific challenge is to asking the model to only answer the question with just a single word. And this kind of the instruction actually do not exist at all in our training data. And somehow the vicuna is also not very good at following those kind of instructions. And these 2 factors adding together prevents the LLaVa actually being able to adapt very well to those academia benchmarks. So one solution we find is to simply mix a small set of the number. Let's say just comparing to 158K, we just mix 1K or 2K of those kind of small short answer questions. This can largely alleviate those kind of issues. So yeah, and the third, I think the other type of this data related challenge is there are some challenge do spatial reasoning, which one is on the right, which one is on the left, or which one, those spatial reasoning related questions, you may need some specific instruction tuning data to actually let the model to understand, because there are not too much of the pre-trained knowledge in both the vision encoder and the language encoder, which you may need to let it learn to. So yeah, I think that's the answer for the first question. Can you quickly remind me about the second one?
Sorry, the second question was, is there a specific data category within the instruction data set? Is there a specific data category that kind of led to these emerging capabilities that that LLaVa demonstrated?
Yeah, I think I do feel we did some small ablation study in our paper, and we do feel that adding the complex reasoning data is really important. adding the like the complex reasoning data actually like it internally incorporates some like chain of thought prompting or answering strategy, where you actually let the model to reason about the images step by step. And we feel that this may, like when we say reason about those memes, it actually tries to like learns like read about those images like pixel by pixel and try to interpret each of the part, and then finally it starts to say like, why is it funny, why is it interesting? And this is about like how, because it can delay its thinking process and just to slow down and think step by step. And the second is that I do feel that some part of the captions may contribute to the like I think actually all kinds of data serves as some pinpoint to align the pre-trained CLIP encoder to the language space. So it's actually not that necessarily our model is learning to read those pixels. It's actually like CLIP already knows like what the character is during the CLIP pre-training, and then by aligning in all kinds of aspects, they are just already there, and the vicuna just learn to read it like one by one, word by word, so that like I do feel that OCR capability is coming from that. And also some recent works also show that if you continue to train your model on high resolution like OCR targeted data, the capability can actually improve. Yeah.
Thank you so much for your answer.
Yeah, thank you.
Great. Can you share your slide to? I don't know.
Oh, sure. I can share the slides too via email and maybe.
That's
Yeah.
great.
Yeah.
Yeah, we kind of a bit, but was any burning question that folks want to ask Haotian before he take up? I see there's a question in the chat. Did you see any kind of immersion properties such as object detection?
That's a very good question. We do we do see that the model can recognize objects by and also like in counting by actually like doing by asking it, prompting it to do detailed descriptions. But current model actually do not have good capability of outputting like object coordinates. And in order to let it output object coordinates, I do feel like you would either need a very strong language model, which you can actually tell it what like coordinates are, and like try to prompt it with some like few shot examples to make it know what you actually mean by object detection. Or there is some recent works like I think Shinkra and those kind of works actually like let you to train with those data. Actually, you just embed the bounding box coordinates into your annotation and let your model to predict those kinds of data. And just by training this, like using targeted data, actually like language model quickly adapts to those kind of new capabilities. Yeah.
Awesome. Yeah, hope that answers your question.
Yeah.
Great. Well, really looking forward to future progress and some of these updates. Keep supporting new open source LLMs, right? As they be released, and hope to see more adoption of the project for various application. Academia and industry as well. Well, thanks both Chang and Haotian for speaking at our webinar series today. We'll have the recording available probably up to 1.5 to 2 weeks, and we'll share the slide of both speakers in the YouTube link as well. Thanks everyone for making the time, and thanks for your attention for this series.
Yeah.
Thanks, guys.
Thank you.
Bye.
Thank you so much.